Hello everybody and welcome back to the MFX Modules series, a collection of useful mini Houdini setups for those who want to get their knowledge on. As always, support is much appreciated. Please like, subscribe, and check the video description for links to relevant project files. Module 4 will cover the activation frame solver and time normalization map. This will allow us to record the frame in which certain attributes cross over a threshold value, and then we can convert that into a map that we can use to get more control and flexibility over our setups. And that sounds like a lot of words, but it'll make more sense once we see it in action. So let's dive in there and check it out. Okay, so in this module, we're going to be covering the activation frame solver. What does that mean? Well, basically, what we're going to do is determine at what frame a mask like this becomes active or reaches a certain threshold. We're going to record that frame so that we can then normalize that activation frame over the length of the entire animation. And so what that's going to allow us to do is to feed the result of that back into our map transition module that we covered earlier on in this series. And it's going to give us a lot of control. So for example, if we wanted to make this, solver go faster in our final animation, we could sit here and change the parameters and resimulate it and reiterate on that as many times as we need to in order to get it. That's fine. But the issue with that is it's not very user friendly. Running a sim, a bunch of times is just kind of a pain. The other thing that isn't really clear to me is like if I wanted to blur this edge more or make the transition width any wider, I don't really know how I would do that at this point without totally affecting the overall shape of the sim. So let's dive in and see how we can get this to work. I'm working off of the project file from the previous lesson where we talked about the pseudo infection, which you can see here. I'm going to just delete the curve and the resample and the carve here. We're not going to need that. We're just going to start with this basic infection system that we have right here. So I'm going to just let this run out and run its course entirely, and we'll see how long that takes. Looks like it's going to need more than 240 frames. So I'm going to just increase the length of the project to 300. And it looks like it's going to need a little bit more. I'll increase the project to 360. Oh my gosh, it needs a little bit more. Let's go to 400. And there we go. We've got everything dealt with. After about, it looks like everything is resolved by around frame 374, but I'll just let it go to 400. It's a nice round number. So now that we have this, we need to put this into a new solver and analyze what frame a point becomes active. So to do this, I'm going to need to set some sort of a condition that governs when a point becomes active. So here, I'm going to just create a wrangle. And I'm going to set a group called active based off of the mask value being over some certain threshold. So in our case, I'm going to say if our f@mask attribute is greater than 0.9, I'm going to say that the i@group underscore active equals 1. So i@group underscore something is basically just setting the group equal to 1. So if I look at the output selection group called active and just scrub through this, you can see that we're starting to get those points highlighted as that mask becomes active. So the next thing we need is a solver to compare our current frame and our previous frame. And if we know that our current frame is in the active group and our previous frame is not, that's the frame that we're becoming active on. And then we just set that. So let's create a new solver. So solver. And we'll just wire this up here and dive inside. So just like in the wet map, we're going to throw it on a wrangle here and wire in our first input. And we're going to compare it with the previous frame here and then output the result. So what we need to do here is check if the second input coming into our wrangle is in the point group of that active group. So we're going to define a integer, and the integer is going to be called a prev. That stands for previously active or active previous or whatever. And we're going to set that equal to in point group. So in point group function is going to allow us to check if a point is in a group in a given piece of geometry. So we're going to be looking in the first geometry, the second input right here. And we're going to be looking for the group name and for which point number we're looking that up on. And so in our case, that's 1. This second input right here is number 1. Then we're looking for the active group for each PT num. So we can determine if we're our previous frame is active. Then we know if our current frame is active and our previous frame is inactive, then this is the activation frame. We're actually on the activation frame. So we can determine that with a simple if statement. So I'm going to go on to the second line here and say if I at group active. So that's saying if our current group is active and not a prev. So our previous group is inactive, determined by this exclamation point here. And we're going to say do something. What are we going to do? We're going to set our f at activation frame equal to our current frame, which is at frame. Now what I'm going to do is I'm going to jump up to the SOP level right here, and I'm going to pin my current view up here, because sometimes the results that you look at while you're down here in a solver, they don't really reflect what's going on up here. And I'm going to do the same for the geometry spreadsheet. So I'm going to hit Alt right bracket, and I'm just going to hit Alt 8 to bring up the geometry spreadsheet down here. You could also just add it from this inspector menu right here. So we've got our geometry spreadsheet up, and we're on frame 1. And if I click play, you can see we have an activation frame that isn't being active. And now that the mask value is growing in some of these points. So take this one, for example. You can see that it's some very low number here, but as it starts to grow up to 1, you can see once it gets to 1 at 0.92, it goes above that 0.9 threshold that we set in here. Once it gets up here, it sets that activation frame equal to this current frame, 135. But then when we move to the next frame, it goes away. It's because it's not accumulating. We're actually doing this check every single frame. And so basically it's going to reevaluate to 0 because none of this is true. So it's just getting overwritten every frame. So what we need to do is something similar to what we did with the wet map and just accumulate it by comparing our current activation frame to the previous frame's activation frame and taking the greater of the two. And jumping up here also, in case you're having issues here, it looks like my geometry spreadsheet's already pinned, but I just want to make sure that when I'm on this, upper SOP level here, that my geometry spreadsheet is pinned. These attributes will read more accurately if I leave this pinned up here, just like the viewport. So jumping back into the solver, we're going to do the comparison. In this case, we're actually going to be looking up the second input again, but we're going to be looking for the activation frame attribute now. So let's say float, and then this one will be called AF prev for activation frame previous. And that's going to be equal to the point lookup on the second incoming geometry, input number 1. We're looking up the activation frame attribute. And we're doing it for every point number. And then here we're just going to set our activation frame attribute equal to the maximum of our activation frame previous and our current f at activation frame. So our activation frame is the maximum of the previous one and our current activation frame. And so this should now accumulate. We should see that this 135 stays there. Once we hit frame 135, this one is going to stay there. So I'm going to just rewind this, and we're going to click play and check out what happens with this activation frame column. Boom, once we get to frame 135, this one stays and it sticks. So nice. We're recording all those activation frames. You can see them popping up in the geometry spreadsheet. We're getting a full readout of all the frames in which this mask became active in our little simulation here. And that's it. So we can now use this to create a normalized map, and it's pretty cool what we can do with that. So let's check that out right now. At this point, you could cache out the results of the solver. I'm just going to throw it on a time shift and wire this in here. And I'm just going to set the time shift to be locked to frame 400. So I just Control Shift clicked on that parameter to convert it to whatever. You could right click and say delete channels and just hard code it to 400 if you want to as well. Whatever works. And just to avoid having to deal with any recooks, I'm just going to lock it right now. So it's just locked like that. Then I want to promote the activation frame to its maximum value to a detail attribute. So we're going to determine that using an attribute promote. This is just going to be the value that we divide our activation frame by to determine what percentage along our map we should be. So here under attribute promote, I'm going to select the activation frame. I'm going to promote it to maximum, and we're going to promote it to a detail attribute. So we're going from point to a detail attribute, and we're storing the maximum. We're going to change the new name to max frame. Let's see, max underscore frame, and we're going to untick delete original. So here, now we can see if we look at our detail attribute. Oh, and my geometry spreadsheet isn't updating because I have this I have this pin in here. So I'm gonna take these pins out now so that we're now updating. So now if I select this attribute promote, you can see that the last frame that gets activated is frame 374. So that's how we know what the maximum frame is. And we can just create a new mask out of this. So let's create it. We're going to create a map for our mapped transition using this max frame and these activation frames. And we're going to do it in another wrangle. So let's throw in a wrangle. Wire that in. And we can calculate this activation map as a percentage. So we're going to use the map attribute, f@map. We're just creating this. Didn't exist before. We're going to make it ours. And we're going to say that the map attribute is equal to the activation frame divided by the maximum frame, the last frame. So f@activation frame divided by, and then we're going to look up that detail attribute by using the detail function, looking on the 0 incoming geometry, the first input there. And we're looking up the max frame attribute. And now if I click the info button and tap on map, you can see that we get this cool looking kind of tie-dye map that illustrates at what percentage in time we arrived at having our mask reaching that threshold of 0.9 that we set in our activation condition. Now we can feed this through our mapped transition module that we created in the first lesson of the series. I'm just going to put my geometry spreadsheet down here, and let's throw down another wrangle. I'm going to label this first wrangle the map. So map, and this one is going to be the map transition. If you were following along in that example, you'll know that I saved mine to a gallery preset. So on my map transition wrangle here, I'm just going to click the gear icon and scroll down until I find my map transition and just load it in there. Now I've named my attribute map correctly according to the way my preset's named. So you just want to make sure that whatever attribute you're using here is the same as that's going into your mapped transition attribute. So we're all good there. So let's go and visualize now. I'm going to hit the info button and visualize the mask. And if we come down here, I'm actually going to just alt click this little thing here and then click it normal to flip it over to the right side, just so we can see our parameters a little bit better here. So on this map transition now, if I drag the position, you can see we get back basically what was going on with our infection, except now we have way more control. We can adjust how sharp the fall off is. We can adjust how quickly it goes. We could actually even set a keyframe on frame 0, and we could say go out to frame, I readjusted my frame from a previous take, but we're going to go out to frame 240. And I'm going to set the position to 1. And you can see here that we're able to just adjust the speed of this. We could even add like a speed ramp into it. If I bring this lower geometry spreadsheet up and click, I'm just going to add an animation editor here. We could even have it ramp to 50% relatively quickly and then kind of do a slow-mo crawl after that. Something like this. A lot easier to work with, and also being able to adjust these fall off attributes. This would be kind of hard to do if we were just working off of the result from our solver, but now we have like complete control over it. So I'm going to just wire this into another little wrangle where we can actually see this thing in action. So let's go and throw it on a wrangle. And we're just going to do the thing like we did before where we bump everything up a little bit. So let's say at p.y plus equals, we're adding to the y position a value that is equal to whatever our mask attribute is. So f@mask times some multiplier times a channel float slider mult called mult. And I'll click this button to bring that mult up, and we'll just set that to 1. And you can see here that It's bringing all that up. And we could go back here now to our map transition and start to kind of, maybe we could do something like we did before where we kind of make it a spring-like behavior with some decay here. And I'll bring this last one down to about 50%, so 0.5. And I'm just going to grab the first one, shift select the last one, and set this to B-spline. So we kind of get that ripply effect going through our geo. I might just now want to make those ripples longer, so I could go back to the map transition and just increase the length of it. I might want to make the whole entire thing go a little bit faster, so we can just bring this into, let's make it only 5 seconds long. Pretty powerful stuff. We could even, like we did in previous examples, if we wanted our map to transition to like be a little bit smoother, we could even at this point go and throw down an attribute blur and blur our map attribute to get a slightly smoother result. And this isn't the only use case for something like an activation frame solver. You can set all sorts of conditions to measure when something becomes active and use it for all sorts of different types of applications. I have a couple examples in the project file that I created, and we can take a look at those. So you can see here in this example, what I've done is I've created a ripple solver where I move this sphere across the water and it activates this sort of rippling effect. And what I could do is right here, I'm going to threshold based off of the speed of each point. So basically what I'm going to say is I'm going to measure the speed and then I'm going to set a mask based off of the speed. If the speed of a point goes above some small number, we're going to set the mask equal to 1 and feed it into our activation frame solver. And then as a result, we're going to get out a map and we could animate that map to move along with our ripple solver to create a mask that kind of follows along with the geometry. So if I visualize that mask now, you can see that as the ripples are forming and moving across the geometry, we're activating this mask attribute. Another example is over here. So we can kind of see what we got going on. In our RBD bullet solver, I'm just going to hit escape and go back to frame 1. Let's just look at what we have. We've got a ball smashing into a wall, like so. And you can see all those pieces are kind of slowing down and just drifting. Now, suppose after I ran this sim, I wanted to shrink some of these pieces away, but only if they had been moved a certain distance away from their start point. So in this example, you can see right here, I'm creating an activation condition by comparing our current position right here, taking the length of our current position and subtracting it from the position of its initial layout right here. So that's what this node is doing. And we're just giving it a distance threshold. We're saying if the length between our current position and the start position is greater than 5, we're going to set an integer attribute on it called activated. We're going to set that to 1. And then here I just have some initialization attributes. Not sure if they're necessary for this. And then here in our solver, we're going to be basically doing that same threshold, saying that in this wrangle right here, we're saying if I at activated, I at group active equals 1. In fact, this probably doesn't even need to be in the solver. This could probably be up here leading into our solver. We're going to set our condition here. Then in our activation frame solver, it's recording on what frame a piece gets to be more than 5 meters away from its start point. And we can kind of visualize that here. What I'm going to do is if we're activated, we're going to compute an age attribute based off of whatever our current frame is minus the frame that we're activated on. And then we're going to create a mask based off of that, where we're going to say that the mask is equal to our current age minus some decay length that we're going to provide down here. So in our case, 36 frames. Over the 36 frames after it becomes active, we're going to get a grayscale value that goes from 0 to 1. And then we're just going to remap that mask like so. So we can visualize that here on the unpack. I wasn't able to visualize the attribute here on the pack geo, but this is just a reference copy of this wrangle here. So if I just play this back, you can see that as they get to a certain point, they start to change color. And that's because they reach that 5 meter mark. And then you could do something like feed that into that mask attribute into a MOPS fall off and have it maybe say shrink away the pieces after they get beyond a certain activation point. And you could use any sort of condition to create this sort of activation. So if we look at those all together, it just kind of does that. Kind of an impractical example, but still cool. Sometimes you just want to be able to make these adjustments post-sim. Suppose this is a really huge sim and you want to deactivate particles once they move within a certain vicinity, but you actually want them to, scale away nicely and not be like abruptly deactivated. This is just a way you could, say, analyze some information from the sim and just create this activation frame post-sim. So again, just giving a brief overview of these two setups from the example file. The example file will be in the description below, but so you can dig in and tinker around with it a little bit more. But yeah, so I hope that this was valuable. I hope that this information is useful to you. It's going to be useful in future lessons that I make, and I hope that you had fun with this, and I'll catch you in the next lesson.